Hello everyone. So today we're going to go over the second part of section 4.2, the second derivative test. So we are given a function f of x here, and also its second derivative. Now we can find the second derivative by differentiating f of x twice, but it does get rather complicated. So in this case, we are just going to be given the second derivative, and that is also true for most of the questions of this type. However, if we look ahead to the third part of the question, it says to find any local maximum or minimum, so we still do need the critical numbers, so we will be needing the first derivative. So we're going to find it here first. Let's see, we have f prime of x is equal to, and then we have 2/3 x to the negative 1/3 power, and then of course 6 minus x to the 1/3 power plus x to the 2/3 power, and then we have 1/3 6 minus x to the negative 2/3, and finally a factor of -1 from the chain rule. So after applying the product rule to the original function and finding their derivative, we can now simplify it. Let's see. So we still have 2/3 x to the negative 1/3, and then 6 minus x to the 1/3 power. And then we're going to combine some of what we have in the second part of the derivative. So we have negative 1/3 x to the 2/3, and then 6 minus x to the negative 2/3 here. Okay, so we can factor out 1/3 from both parts, and also x to the negative 1/3, and also 6 minus x to the negative 2/3. Now let's see what is left over. You can see that we are left with 2, and then 6 minus x from the first part of the, sorry about that, from the first part of the derivative. Just going to move this slightly to the right. We'll be needing that table later. And then subtracting that, we have x, right, and that's it. So that's a result from factoring that we have. And now we can simplify what's in the parentheses a little bit. Let's see what that gets us. That will give us, in the end here, 12 minus 3x. Notice that both 12 and 3x have a common factor of 3, which conveniently eliminates 1/3 at the start of the derivative. So we will have x to the negative 1/3, and then 6 minus x to the negative 2/3, and finally just 4 minus x. Okay, now generally we can write a derivative like these with no negative exponent, so we'll be doing that here. And so we have 4 minus x, and then x to the 1/3 power, and then 6 minus x to the 2/3 power in the denominator. All right, so now if we were to differentiate this, we will have to apply the quotient rule and then also the product rule to the denominator. So it does get a little bit tricky, but the second derivative is already given to us here at the top of the question. So we'll just be using that for part A. So what does that mean? Well, notice that possible inflection points is either where the second derivative is equal to 0 or where the second derivative is undefined. So that will help us locate possible inflection points. Okay. Now, given our second derivative, the expression is never equal to 0, so this will provide us with no solutions. However, as we can see, if x is equal to 0 or if x is equal to 6, the second derivative becomes undefined. So we have 0 and 6 here. So what we're going to do is kind of like what we did with the critical numbers. We're going to put it into this table here. So we have x is less than 0, then 0, then x is between 0 and 6, and then when x is equal to 6, and finally when x is greater than 6. And we're looking at the behavior of the second derivative, and that is whether it's positive or negative in those intervals to see if the function is concaving up or down. Okay, so just by substituting negative values in for x, the term here will be positive because it's going to be raised to the 4th power. So it will be positive first. Oh, sorry about that. Just kind of made a mess. There we go, that's better. And then if we substitute a negative value here, it's going to be subtracted. So it will be greater than 6. So both these parts will be positive, but the numerator is negative. So overall, the second derivative will be negative in that interval. So the function is concaving down. Now here, the second derivative is undefined. And let's continue. Let's say if in this interval x is equal to, for example, 1, this first term is positive, this second term is also positive. So again, the second derivative will be negative in that interval, so it's still concaving downwards. So what that tells us is that the point at 0 is not an inflection point because the concavity does not change. And then we have x equals 6. Again, the second derivative is undefined. And then when x is greater than 6, this first term is still positive. However, the second term will be negative, and if we have a negative numerator and a negative denominator, the second derivative overall will be positive, so it does change concavity at 6. So if this point exists, then it is an inflection point. Alright, so if we were to substitute in 6 into the original function, we have 6 minus 6 is 0, and then 6 to the 2/3 power is a number. So overall, we have 0 as a result. And that is to say that we have an inflection point at 6, comma 0. All right, so now finding inflection points also completes part 2, or part B, sorry. And that is to find the intervals in which the function concaves up or down. We actually have it listed already, so it probably is a little bit better to write out the result though. So we're going to go ahead and do that here. So where does the graph concave down? Well, the graph concaves down from -infinity to 0, and then also from 0 to 6. And the graph concaves up from 6 to infinity. All right. So again, that's just from reading the table from part A. And finally, it says for part C to use the second derivative to find any local maximum or minimum. So to prepare for that, we first have to examine where the first derivative is equal to 0 or where it is undefined. So the first derivative is equal to 0 at x equals 4. And the first derivative is undefined at both 0 and 6. Okay, so x equals 4 will make the first derivative 0, letting x equals 0 make it undefined, and letting x equals 6 will make it undefined as well, as the arrows indicate the relevant parts of the derivative. All right, so we have then another table to fill out with the information that we just got. So we have here 0, 4, and 6, right? We have 3 critical numbers to look at. So the number line is being cut into 4 parts. First is x is less than 0, then x is between 0 and 4, and then x is between 4 and 6, and finally x is greater than 6. Now, we could look at where the graph concaves up or down. That's one way of doing this question. So, but that's a little more challenging if let's say for example, at 6 and 0, the graph neither concaves up nor down. So we couldn't just rely on the second derivative test. We actually have to go back and use the first derivative test here as well. So let's see. The first derivative, and then the original function. Okay, when x is less than 0, this part is positive, this part is negative, and this part is positive. So overall, it is negative. And so the graph is decreasing. Now, at 0, the derivative is undefined. And between 0 and 4, so let's say, for example, x equals 2. So the numerator is positive, this is positive, and this is positive. So overall, the derivative is positive, and this will be increasing. Okay, so even though the second derivative test doesn't tell us directly that this is going to be a local minimum, the first derivative test does tell us that that's what it is. And in some cases, it'll be necessary to kind of do both. So a local minimum, and this would be at 0, 0, right? Because the function goes from decreasing to increasing. And then here at x equals 4, the derivative is equal to 0. So that's the other kind of critical number. And then we're looking at x between 4 and 6. So maybe x equals 5. So this is negative, positive, positive. So overall, the derivative is negative. Okay. So that means this is decreasing. And of course, this would produce a local maximum at 4, and then 2 to the 5 over 3. That one's a little bit tricky. And then when x is greater than 6, this would be negative, this would be positive, and this would be positive. So overall, the first derivative will be negative there. So, oh, yes, that's decreasing, which makes sense because we know here that this is going to be an inflection point already. So now, it's also a good idea for a question that is so rather complex like this one, to look at the graph itself and see if it kind of matches our expectation based on the math that we did. And that is to say the first and second derivative test that we've done. So just going to go ahead and show that. Okay, just give me 1 second here. Okay, ready. Or sorry. So here's the function. So we do have the local minimum at 0, 0. We have the local maximum at x equals 4. And here we have the inflection point as 6, 0. So those match all the inflection points and local maximum and minimums that we found. And so that's good. So again, for a question like this, you will be given the second derivative. However, let's say if the original function was a polynomial, then, well, the second derivative would be a lot easier to find. So in those cases, you will not be given the second derivative. Okay, so just the one example today. Hopefully that was useful. And that's it for today, so thank you for listening.